So how many of you guys know quantum mechanics or have taken a quantum mechanics course? Okay, cool. So we're going to go over the basics of quantum mechanics. So what quantum means is just discrete. That's what the word means. And it deals with the smallest units of matter, of objects in the universe, subatomic particles, deals with things at a very small distance. And weird things happen at this distance, such as particles could behave like waves and wave behaves like particles. They become pretty much indistinguishable. So like some of the effects of this is, let's just say this eraser is a quantum particle. If I throw it at a wall, sometimes it will get reflected, but sometimes it will go through. It will pass right through the wall. That's just, I mean, it goes against our basic understanding of how walls work. And more non-intuitive, like I feel like this is more bizarre. If we have, this is a quantum-sized object, and we roll it off a table, every time just a macroscopic eraser will go off the table, but sometimes it'll get reflected back. Now the best way to understand this weirdness of what happens with quantum mechanics is to view an experiment. So I'm gonna go over the double-slit experiment. So where we have a detector and we have a screen with two slits in it. So if you throw classical balls, what happens is at the end, so the detector at the end will measure the ball being here, will measure the ball being here. Now let's look at classical waves. If we have a single slit, what happens to the waves? The wave will come in and hit the detector pretty much at 1.2, the most intense point. It'll have like some like fuzziness around the edges of this point, but that's just because of the it's decreasing in intensity. If you put two slits and we put two classical waves going in, what we get is called an interference pattern, where you get bright spots on certain areas of the screen and dark spots on the other. And that's just when the two waves meet up, when their wavelengths or amplitudes add up. So for example, let's just say one wave is represented by a cosine. This is 1, this is -1. And then the other wave, it hits at the same angle, so let's just say that this angle is just theta. Get 1, -1. You know, when you add them together, 1 + 1 = 2. You know, 0 + 0, so it's pretty poorly drawn. But so these are the same point, -1 + -1 = -2, and so on and so forth. So this is constructive interference. So when the waves are at the same angle or at an angle of +2 pi, you'll see this constructive interference. However, let's just say instead of 2 pi, you get pi. So we're going to shift this wave over. So we're gonna shift it over by pi. We're going to get, so now when we add the two waves, -1 and 1, that's 0. This, like I said, so this is the same point. So 0 + 0 is 0. 1 + -1. So pretty much it's just 0 everywhere. So this is destructive interference. Now let's make this particle quantum mechanical. So let's just shoot two quantum mechanical particles, and like I said, they behave like waves. They have this wave nature to them. So when they hit the side of the screen, they'll also exhibit this interference pattern along the edge. Now something that's weird is, so they behave like waves in this situation when we just shoot them, where we have just a beam of electrons shooting this way. However, if we decide to place measurements, measuring units over here, detectors over here, to figure out when the electrons go through, or precisely what happens, measuring just the electron's movement, what happens is it goes back to behaving like two classical balls coming at each other. So through the edge. And this is weird because it's just like, okay, so the physics in one situation when you don't measure it It's completely different from what happens physically when you do measure it. Now, what's even more bizarre is if we shoot one particle at a time through this. So it could either go through this one or this one. What happens is we still get the same interference pattern on the opposite edge. So, but this doesn't make any sense because there's one particle going through the slits. You know, there's nothing for the particle to interfere with. So we say that the particle, so let's say this is slit 1, slit 2, it goes through both slit 1 and 2 at the same time and interacts with each other. And if you put a detector on one of them, then it goes back to behaving classically. So when you know which one it goes through, it becomes a classical, it acts classically. But if you don't know which one it goes through, it is quantum mechanically. So we could describe this uncertainty with a state. So we could say, there's like a probability, let's just say, C1 that it goes through the first slit, and C3 which goes through the second slit. And so this is, so if you guys heard the Schrodinger's cat, this is very similar. So you don't know whether the cat is dead or alive, so you have this function, this is dead, this is alive, and you have a probability of each. So, let's just say it's like equal probability. So these constants are just coefficients, they're just 1/2, 1 over the square root of 2, 1 over the square root of 2, because how we get the probability is we square the coefficients, and this has to equal 1. So, and it depends on the experiment. So let's just say, if the cat's in a box, you ventilate the box, you put food in the box, the cat's happy, most likely it will be alive. You'll probably have something like this, 3/4, or 2, alive, and then dead. Or, if you just decide, kind of a conceptual idea of what happens in quantum mechanics, I want to go over the mathematical framework, or just briefly introduce the mathematical framework that goes along with it. So the first one is called the Heisenberg's uncertainty principle. And so the change in x, so the change in position, times the change in momentum is greater than h bar over 2. Now, h bar is called the Planck's constant, and it just has to deal with, it's just a constant involved in quantum mechanics. In quantization, you'll see it as a much stronger interpretation when we get to string theory, but for now it's just a constant that appears within quantization. So you have also, so this is the first uncertainty principle, also the second one is delta E, delta T, 3 and h bar over 2, which we'll come back to this later. But for now, let's just look at the delta x, delta p equals h bar over 2. So this just means that you can't be certain about its position. So the more certain you are about an object's position, the less certain you are about its momentum. So we can even use this as an example. We don't know about its position, so there's a nice spread out momentum. We could measure the momentum of these waves, these particle waves. However, when we measure the position, we just get 2 dots. We have no idea about its momentum. We have no idea, there's no way to tell its momentum when it's just there's a single dot indicating that it passed through there. Next thing I want to talk about is commutation relations. So what that is you just have x, one variable, p, and mathematically this just equals to x, p, so it's the first term times the second term minus the second term times the first term. And this is all mathematically the statement means. Now, classically, this will be equal to 0. Because let's just say we're driving a car and we have a speedometer in front of you and we have a GPS in the other place, right next to it. So if we look at the GPS first and see that we're 5 miles from home, and we look at the speedometer that says we're going 10 miles per hour, if we look at the speedometer first, it'll still say we're going 10 miles per hour. To a very good approximation. And if we look at the GPS next, we'll say it's going 5 miles per hour. So that just equals 0, classically. However, as we saw here, making a measurement of its momentum will change its position, and making its a measurement on its position will change its momentum. So this is not zero in quantum mechanics because just like the act of measuring changes the state. So we say the difference between these measurements is I h bar, and I is just the square root of -1. So
I have a question.
yeah.
So you were talking about the order of the measurements.
Yes.
So then the first term means you measure the position first, and then the momentum secondary.
Yes. Unless I mean I might have screwed this up. Did I reverse the order?
No, that's.
Okay. Yeah.
Okay.
So,
yeah.
yeah.
So I know their computational relation that
Yeah.
work. Yeah, but I just know that it's come from like so then the characteristic from matrices or the operator.
Yeah.
But so if you're talking about the order of the measurements, so then I don't get the what you mean.
So okay, so here we can define just x as x, and we can define p as h bar over I d by dx. Okay.
Okay. Yeah.
So now let's just say we have a function, we have a state. So we have x, p. We act on a state, so we have x, p minus p, x, f. So now we get x, h bar over I, d by dx, f minus d. And now, see this is where it comes in, so be careful here. So h, I. So now I x on the position, and I x on the function as well. Multiply by the function. So now if we calculate it, run through a quick calculation, we use the product rule, or the product rule. So this is just f of x, and then minus h bar over I, and that's just, so it's x. So we act on this first, and then we add this. Is everyone familiar with this rule? Okay, cool. So then we add d by dx. So these two cancel out. You'll have to put a I h, negative I h. If we multiply top and bottom by I, we get -1, so h, I, f. And then, so x. And then cancels out. So it's a property, so these are operators. So okay, so the main statement I was trying to get at is classically, these aren't operators, they're just variables. They're just, there's properties of the state. But now we actually operate on the state to get the quantities. So, if we operate this on the state, we get the position. If we operate this on the state, we get the momentum.
Probably the question probably was there is no time ordering in this, right? Like you don't do the first operation and come back, so there is no time involved.
Oh no, there's not. But this is actually, time ordering is very important in quantum mechanics. So, or not in quantum field theory. So, I'll give a brief example later, but in quantum field theory it plays a huge role in how we order our operators, because if we put the operators out of order, then so right now I guess if we do this the opposite order, just a negative sign will come out of it. But when we go to quantum field theory, for example, when we have a field with no particles in it and we start making these operations, it would it would be a completely different state. It'll mess up the state. So we'll see that later on in the course. For now, sorry if I just went off on a tangent, but so that's good for people who haven't seen this before. So okay, so these commutation relations are very important. So it's what makes, so if you have a classical theory and you impose these commutation relations on your theory, it's quantum mechanical. You make it quantum mechanical. So they're very fundamental to your formulating the theory of quantum mechanics. So the next thing I want to talk about, for those who haven't taken quantum mechanics, is particle in a box. And this is the first thing you'll talk about when you study quantum mechanics. So let's just say you have a box or a region of space. These boxes aren't real. It just represents a region. We'll start studying boxes, asking where they came from, if they're fundamental or not. But for now, the box just represents a region of space. We say the length is A, and this is the endpoints. So a big thing about this interpretation, or this model of a quantum particle, are the endpoints must be fixed at 0. And this represents a probability wave. So the probability that, let's just say an electron, the electron will be found in that box. We'll have max probability over here. Having maximum, okay. So, and let's just say this is energy 1. So the second energy it could occupy, and this is where quantum comes in, because it could only occupy a certain discrete quantity. With that, that's energy 2, energy 3, and so on and so forth. And these energies has a simple form, just n, that's just the energy number, a squared c. And c is just a constant, it depends on the particle. Let's do a quick calculation. So let's just say a equals, the length of the box just equals 1, just 1 unit. So let's calculate the energy. So the first energy for this particle is just, we plug in 1 for A, 1 for N, so that just gives us C. Energy 2, plug in 2 for N, that gives us 4. Let's just say we double the box. So we double the region in which this particle could live. We get C over 4. And then for the second energy level, this energy, we get just C. So let's take the difference of the energies. So for this one, the difference of energy is 3C. And the difference of energy for this one is just 3/4 C. So now we can see from this example that the less certain you are where your particle is, the difference of energy. So the larger the box, the larger in which area of the particle could live, the less of a difference there is between the energy levels. So I mean, this isn't, so energy is, it's defined different from momentum, but they have relationships to each other, direct relationships. So this is just an example of the uncertainty principle. The next thing you'll come about is a quantum harmonic oscillator. And this is just another way of modeling a quantum particle. I think I spelled that right. Oscillator, yeah. Okay, so instead of dealing with a box, we just say, there's some potential. And we write the states in this notation. So this is the ground state. We say this is 0 state. This is the first state, the second state, so on and so forth. And the energy level is given by the state is just E h bar omega n plus 1/2. And omega comes from the potential. So it comes from, so you have an energy solution called a Hamiltonian, and then you just, which I'll talk about all this later for those of you who don't know where potential comes from, but this is just, this omega deals with potential, but that's not important for now. So this is a more, I guess you could say, a more fun way of getting from one energy level to the other. So you have something called raising and lowering operators. So if we act on a state, so let's just say we're at the first state, and this is a raising operator, we get the state 2. So we go from a lower energy state to a higher energy state, and we get a factor a normalization factor that comes out of it. So it's defined a n goes n plus 1 in the state n plus 1. And then the lowering operator, vice versa, you know, if we have the state 2 and we get back 1 with a normalization factor of the state, so 2. So a n is just square root of n minus 1. So is everybody clear? No, you're not?
I'll get there.
No, it's cool, it's cool. So, no, because this is important. So,
Because this is like direct notation too, so like a lot of people haven't been exposed to it.
Yeah. This is the
yeah,
first time being
so as far as now, so these are just ways of labeling the state. So this is just a label for the state. This is just a label for this energy. Really just a label for the energy. I mean, there's more that comes to it, but when we calculate the energy, we just get a certain energy value for each state. And the energy value is given here. So for this state, like what does n equal?
that state.
Yeah, so 0. So this is the 0. So n is in here. So n equals 0 equals 1/2 h bar omega. So what's n up here?
1.
Okay. So that's E equals 1, so 3/2 h bar omega. So if I want to, so this is to raise the operator. So what state do I get now? No, it's not 1.
It's 2.
Yes.
Because you're raising it?
Yep.
Okay.
If it was just A, you're not raising it, right? What's the just A then?
And
Oh, you lower it.
You're lowering.
Yeah, so it's n minus 1. So sorry, I put A, so I added on the second state and I got the first.
okay.
So if I do this, what would be the state?
That's a big one.
I don't know. It's intimidating.
153.
This is, so if it was this, it would be 153.
Okay. So it's lowering.
Yeah.
So it's 151.
Yep.
Perfect.
Cool. And also, so these factors come out, these normalization factors. They're just to make sure that everything is consistent. So the theory lives in a space called a Hilbert space, and things which we're not going to go into that in that detail now.
Can A operate on 0, or is that just not defined?
Okay, so when A operates on 0, you pretty much kill your theory. You get rid of your theory. That equals 0. That just equals, so the lowest state is A equals 0. Okay, so that comes important later. So is everybody comfortable with raising? So all we do is, we have this object, this cool object that adds 1. We have this cool object that lowers 1. So now let's look at these normalization factors. So let's just say we have a state 3. And we operate the lowering operator and then the raising operator. So we operate from right to left. So we operate this one first. So we could leave this out for now, A over 3. So what does this equal?
14.
So-
3, 2. Which one?
Yeah. So square root of 3, because this is n. Square root of 3, 2. And now we're going to raise it again. So we're going to raise the state. So we could pull out the factor of 3, because that doesn't play a role in this operation. We're going to operate like a surgeon or a doctor on this state. So what does it state?
3, 3.
3.
3, 3.
So this just gives us the square root of 3, and then we add 1 to this state, so we just get the state 3. So now once we multiply by this factor of 3, we get 3, 3. So a special property of these two operations being put together is called, so what it does is it takes a state and it gives you the number of that state. So let's just say this is n. So it returns the same state, so it doesn't, because you know, you lower the state and then you raise it again. So you just get the same state, but the factor that comes out in front, for you who are in math, the eigenvalue, that is just the number, that is just the, what number the state is in. So this is called a number operator. You know, what's the level of the state? So you know, just as we saw here, we did lowering operator, raising operator, acted on state 3 and got back 3, 3. So it tells you the number of the state. And like we said, like there's this abstract notation that numbers equal this. Something weird I want to point out right away is that the lowest state it could have, so right now, I mean, let's just say, you know, taking gravity aside, I'm just standing still. Like, what would my energy be?
0.
Yeah, so 0. So it's weird now that once you get into the quantum mechanical level, in order for the particle to exist, because if it goes lower than 0, it doesn't exist. So in order for the particle to exist, it has the energy 1/2 h bar omega. That is just something very strange about quantum mechanics. And you know, as we'll see later, it pretty much like this uncertainty gives these weird effects. So next thing I like to go to is I like to give the example. I like to show, so if there's 2 plates and they're conducting, they're neutral, they have no charge, and they're really close together, and they're in a vacuum. So do you guys know what a vacuum is? So it just, does anybody? Not you. Okay, so all a vacuum means is it is just the absence of particles or absence of energy. So there's nothing in the vacuum. So there's nothing around, like nothing's possible happening here. So classically, the energy will just be 0. Nothing happens. So what would happen to these 2 plates that are neutral, so according to Maxwell's equations, they don't experience a force? What happens to them?
Nothing.
Nothing. Cool. So that's what we think. That's what, you know, if you're at the toddler when you were examining the universe, you would say that nothing happened. So what actually happens is these plates attract each other. And that is because the plates are in such a small region, so they're so close together that the laws of quantum mechanics, so you have to take quantum mechanics into account now. And one of the uncertainty principles is a change in energy is a change of time. So you can't be certain what your energy is time. So for a small amount of time, energy just pops into this vacuum. So it perturbs the vacuum. So we have a vacuum with no particles, but because we're so close, because we're looking at a scale so close, what happens is energy just pops into existence. And they are taking the form of virtual particles. So we have virtual particles popping in and out of existence in this vacuum on the inside and the outside. And because of this boundary condition, the number of possible virtual particles could exist is higher on the outside than on the inside. So it causes a pressure and pushes the plates together. So yeah, so this still, I mean, the more, like, you can just think about it as much as you want. Doesn't really make sense. But what will help is to have some mathematical background to it. So this is where I like to get into quantum field theory. And this is a result of quantum field theory. This is, I mean, the experiment has been done. This is true. It rains legit. So we this whole time